Yeah. Venki's joking that I'm already becoming longer. You see, I have a long last name finishes with IAM, so I'm already almost there. I eat more spicy food than he does. So next time I come, I have to pick up one of the languages I have decided already. Okay, so here's what I'm going to do. I'll talk about generalized Radon transforms. The talk would be, in some sense, complementary to the talks of Dr. Bowman that you heard today and will continue hearing. But it would be different in a certain way because Professor Bowman is going to talk mainly about the micro-local aspects and the recovering singularity. I will be talking mostly about exact reconstruction formulas, something related to the description of the range of these transforms, some stability and numerical implementation issues, and I will be talking a lot about applications. In fact, I want to start my first lecture with a lot of applications and pictures and motivation. Today you won't see much of hard math, and this is the last talk today, afternoon talk, so I decided to make it a little bit more fun. Tomorrow my talk is in the morning, so there will be more math tomorrow. But I will be talking about at least 4 different types of radon transforms, and I want to make sure that they don't come out of the blue, that there is some motivation behind it, that all of you would understand that we're not making things up just for the fun of it, but they do have some applications in tomography. So this is a very rough outline of the lectures. In lecture 1, I'll, as I said, talk about imaging modalities, give the definitions of these generalized radon transforms, and formulate the relevant mathematical problems. Lecture 2 would be about uniqueness, injectivity sets, and inversion formulas and algorithms. Lecture 3 would be range descriptions, micro-local regularity, and numerical implementations. And I'm absolutely sure that I won't be able to stick to the time. So whatever is not fitting in this would go to lecture 4. If I do fit in time, there's plenty of other interesting stuff that I will talk about in lecture 4. So let's start with some vocabulary, some motivation. Tomography, of course, as any other word in science, comes from Greek words. Tomos in Greek means slice. Tomography is the science that reconstructs the images by slices. Although there is something called fully 3D tomography, where people recover 3D images without doing slices, but they visualize them by slices anyway, because on the computer you cannot see 3D unless you do slices. So anyway, even the 3D tomography is called tomography with the word slice. So there are different types of tomography. For those of you who have been in the field, this is probably very well known, but for those who are new to the field, you'll be amazed with the amount of different words that people use with tomography. This type of tomography, that type of tomography. I don't know. You will try the combinatorial analysis from these 3 things and see how many types of tomography you can have. So I tried to somehow systematize the different types of tomography. They are different, first of all, by the physical nature of the input and output signals. What does that mean? So tomography is usually you're trying to recover an image of something that is in a black box, something you cannot reach, something inside the patient, inside the engine of the rocket, under the ground, and so on. Because if it's visible, then why do you need tomography? Just photograph it. Right? So what do? You send some signals, and then you receive some signals, and depending on the physical nature of those signals, we distinguish different types of tomography. So there is the electrical signal that you measure current, apply voltage, or the other way around. There's optical tomography where you shine a laser and then the light is scattered and you measure the scattered light. Acoustic tomography, this is the sonography that people have been doing forever when they image babies and so on. The thermal, when they heat up the tissue, certain things happen. Magnetic tomography, magnetic resonance imaging, MRIs, many other things. There's elastography, where they put the patient in some sort of device, let's say an acoustic device, and the doctor is pushing with his hand, creating some elastic waves and seeing what's happening and so on. Many different types of tomography based on the physical nature. People distinguish also on the interaction of the signal with the medium. In other words, how does the signal go through the body and what part of the signal do you measure? Emission tomography is when you feed the patient with a drug that it has some radiation, some isotopes, and then the drug goes, the patient digests, and then they put the patient inside the device that measures the radiation that comes from inside the patient, right? I mean, hope everything is measured to the point that you don't kill the patient by this drug, but that's what they do, and there are different reasons for that. They try to tie this radioisotopes to sugar, and sugar tends to go to, let's say, cancerous cells immediately, and if there's cancer there, inside the patient there is a very bright region, and they would know something is wrong there, let's go and look carefully and so on. So emission is the radiation, the signal is coming from inside. Transmission tomography is the standard X-ray tomography or CT scans where you send X-ray and the X-ray goes all the way through and you recover what is left out of it on the other side. So that's the transmission tomography. Scattering tomography is you send some sort of signal, acoustic or light or optical signal, and it scatters, and then you collect the scattered signal, try to recover what was happening inside. Reflection is when you send acoustic signal and you listen to the echo coming back, diffraction, absorption, and so on. And then applications, of course. There is tomography in medicine, there is tomography in archaeology, in biology, geology, material science, military industry, and I'll try to show you some pictures of several of these so that you see. So you can have, I don't know, acoustic reflection tomography in medicine, or optical scattering tomography in, now you can try with all the combinations and see how many versions you can come up with. Okay, so I tried to just give you some images just to have some sort of idea if you haven't seen any of this. So this is a CAT scan, the computer-assisted tomography. This is the X-ray tomography, transmission tomography, where you create the 2D slices of a 3D object. This is a brain image cut across the vertical, perpendicular to the vertical axis. If the vertical axis is the spine, and this is something typical that you can see in the hospitals. This is something that people use in geophysics when you're trying to recover oil wells, for example. They create signals, they get echoes, and they're trying to recover the location of oil or other minerals. It's very interesting the way they create these signals. I live in Texas now, and in Texas, very recently they discovered huge resources of natural gas, and now they're exploring it. In fact, my university is the biggest owner of land in town. So they, and the way they pump up, get the gas out is they don't know where exactly it is. So they're giving money proportional to the amount of land that you own. So now University of Texas in Arlington is getting a lot of money for natural gas because we have a big land. And they're looking for it, and it was very interesting. So one day somebody came and knocked my door and suggested, he was representing a company that is looking for this. So he said that they'll give me $100 if I allow to put a small device in my front yard. And I said, I was not sure. I said, wait, what device? Just make sure that you. So apparently they're putting this, basically a microphone, about something larger and something more crude. But they were putting this microphone once every 100 meters. They were all connected to each other. It was an array of microphones. And then about 5 kilometers away, they put this huge machine that I cannot even call it a tractor. It was like a gigantic thing that was hitting the ground physically. And it was creating waves in the ground 5 kilometers away. And they had this array of microphones sitting all around my city. And they were collecting basically the echoes. And then using that, they were trying to come up with an image like this to know where exactly they should go and drill, because drilling holes is very, very expensive. And of course, all of that, I hope, was done, after they collect the data, there's some math involved, and you will hear part of this, and I think next week, Professor Cliff Nolan will be talking about subsurface imaging. At least part of his lectures will be about that. So you will see a lot of things about this. Radars, this is an image of the most famous, probably, Hurricane Katrina that ruined, unfortunately, New Orleans, but the radars, the meteorological radars, are also done through this type of technique when you send some signals, receive some signals, and then you try to recover the images. So this is probably the most classical thing, the CAT scan, and I want to get to some formulas and show some sketches here. This is, see the same skull type image. So what happens is, you have this device, this is, if you haven't seen this, it's basically a big donut-shaped object. There's a table here, the patient lays in this table and then goes in. There is an X-ray source going around this pipe, and it sends an X-ray, and then there is a detector here, and that detector measures the intensity. They know the intensity that they send, They measure the intensity that comes out, and they try to recover the image of the cross-section of the patient's body. In this case, it would be the head. This is the doctor sitting here and seeing the image on the screen. So how do they do this? This is a very, very simple sketch. So let's say this is the cross-section of the patient. This is the source of the X-rays. The X-ray goes through the body. They know the intensity. They generated it. They know how many photons the intensity is. For the simplest case, the number of photons flying out of the source per second. And then they have a detector that measures the intensity. Clearly, when the ray goes through the body, the intensity drops. So the only thing that they detect is the drop of the intensity. They know the I0, the intensity here. They know I1, the intensity when it goes out. And physicists know a very simple rule called Beer's law, B-E-E-R with a capital letter, has nothing to do with the drink, which tells you how the intensity drops, how the intensity of the X-ray drops. So it says that the intensity, the change of the intensity when the ray travels distance delta S is proportional to the intensity itself and something called absorption coefficient. Of course, the negative stands for the fact that the change in the distance is positive, the drop in the intensity is negative. So if you make things infinitesimally small, you get a differential equation, in fact, separable and everything. You just integrate, and you immediately see that because you know I1 and I0, you know the final intensity and the initial intensity, the right-hand side is completely determined. So what you measure is you're measuring the integral of this absorption function along the line L. The line L stands for this line here. By the way, X is a two-dimensional variable. It's a function of X1 and X2. And of course, the goal here is to recover this absorption function. So what the doctor is looking at here, this image that the doctor sees, is simply the grayscale image of this function of two variables, right? So it's a function where the color of every pixel corresponds to the value of the function, with x1 being this x is next to this x. So the goal is to recover this function. And of course, just knowing one integral, you cannot recover the function. It's a two-dimensional function, but even if it's one-dimensional, knowing the integral doesn't give you the function. So what they do is they do parallel shifts. So you measure along this line, then you measure along this line, then you measure along this line. So you measure the integral of that function of two variables along all these lines. Then you rotate. Then you would have the integrals of that function along lines like this. Then you rotate a little more, then you have integrals along the lines like this. So theoretically, you can assume, that you have the integrals of your function along all possible straight lines. And you want to recover the function. Now, in reality, you don't have all lines. You have a fairly densely discretized version of all lines, discretized in the angle, the rotation angle, and the distance. And that's another problem. It's another question whether this discretization affects anything mathematically or it doesn't. Of course, we're assuming that the function is compactly supported, right? The whole function is sitting inside here. Everything outside is zero. So the integrability and so on are not issues here. We don't have this issue. So, too much. So that motivates the first definition, the ordinary. I put ordinary in parentheses. People don't usually call it like that. I call it ordinary because I'll be talking about three other ones just to distinguish. The ordinary Radon transform is a transform that eats a function of two variables and spits out its integrals along straight lines. So the Radon transform has two parameters. These two parameters parameterize the family of all lines. So for the given function of two variables, you put into correspondence its integrals along straight lines on the plane. So let me very briefly talk about the parameterization of the lines on the plane. There's many ways, of course, to parameterize the lines on the plane. The most useful one for these purposes would be parameterization like this. We parameterize it with the normal cosine theta sine theta. So omega is the normal to the line, and d is the distance. So theta and d define a line on the plane. So you can easily see that the family of lines on the plane is two-parameter family, and we're trying to recover a function of two variables. I want to remind everybody that yesterday, if you were listening to the talk by Professor Rakesh, he was saying that every time you have an inverse problem, it's a good idea to think about dimensionality so that you can see the complexity of the problem. Here I'm trying to recover a function of two variables from data that I measure that is also two-dimensional. So the RF of theta d is the data that I have, and what I want is f of x. So in some way I want to invert this transform. The big question for creating images in CT, in computer tomography, is related to the inversion of the Radon transform, coming up with a function of two variables from data that is two-dimensional itself. Now, again, a couple of things, I want to make a couple of comments here. You see, the convergence of the integral is not an issue because the function is compactly supported, but if you for a second forget about tomography and think about this as a purely mathematical problem, there's all kinds of questions you can ask now. You know, you can now assume that your function is not compactly supported, but decays sufficiently fast so that the integrals make sense. And then you can think of function being not just a two-dimensional function, but three, which would still make sense for applications. But for purely mathematical reasons, you can think of also Rn, and then try to invert the function from the Radon data and so on. So there's some vocabulary issue. The transform that integrates along straight lines is usually called X-ray transform. The word Radon transform, if I'm in Rn in general, is a transform that integrates along hyperplanes. So for example, in R3, the word Radon transform means transform that integrates along planes. If you want in R3 transform that integrates along lines, we call it X-ray transform. And of course in R2, these two things coincide, right? So just so that you know that the word Radon transform in this case is the same as X-ray transform. Okay, so let's move forward. So I wanted to show you a typical image of the Radon data. So this is what people call a Sinogram. So this is an image. What you see is that the image of RF theta d. So RF of theta d. So that this image here corresponds to the Radon transform of some function. This axis corresponds to periodicity. So this corresponds to the angle, say from 0 to 2 pi, and this corresponds to d. And from this, and of course, as I said, every pixel here, the location of the pixel corresponds to one fixed value of theta and one fixed value of d. And the color of the pixel corresponds to the value of the function, right? So having this picture, I want to have a picture of the original, what people call phagon, so the function. This is RF, and I want F. So the first question for today is, what is F? Can anybody tell me, just looking at this? This is the Radon transform, so the function is... It's impossible to say, I'm joking. if you guys could do that, then you know, every hospital would love to have you. The whole point of doing what I'm going to do is because just looking at this, it's impossible to say what the function was. So here's the function. So there is no way to look at this and say that the function looks like this, right? It's a simple thing, it's just some circles, a union of circles. The values, the colors correspond for the values. But you can imagine, I mean, if you have a real patient with some structures, the Radon transform is going to be something crazy, and you want to recover the function, you cannot, right? So you need to develop some sophisticated math technique. But again, the vocabulary is, if I say phantom, I mean the graphical representation, the numerical representation of the function f, which I'm interested in. If I say Sinogram, that means the graphical representation of the Radon transform. Okay. So what kind of problems do we have? Again, from Professor Rakesh's lecture, guys, you heard that there are some absolutely standard things you need to do whenever you deal with inverse problems. The first thing is injectivity. Do you have uniqueness? Because if you have two different functions, f1 and f2, that are different, for which RF f1 and RF f2 are the same, well, how do you invert? I mean, if you have two patients that are different, but the data you measure is the same, then which one's picture are you recovering, right? So the first question is uniqueness of reconstruction. Do you have enough data to claim uniqueness? The second thing is also very interesting, reconstruction formulas and algorithms. You may say, well, if I have uniqueness, what is the second about? A lot of times, very often, this uniqueness results are qualitative but not quantitative. I mean, you know, for those of you who have taken, or probably everybody has taken ODEs, like the first theorem that you show the uniqueness and existence of some first order differential equation satisfying Lipschitz conditions and so on. You probe it for 3 pages, but it only says that the solution exists and it's unique. It doesn't tell you how to find it. And the fact that you know that there is an inversion doesn't mean you know how to do it. So the second question is how to do it. What are the reconstruction formulas and algorithms? Very, very non-trivial thing. Again, by the way, guys, for the regular Radon Transform, everything I'm saying has been done long ago. And some people got Nobel Prize for doing some part of it. Really, Nobel Prize in medicine for solving a mathematical problem, which, by the way, has been solved many times before that guy got the Nobel Prize for solving that problem. But the reason I'm emphasizing this is for many of the other Radon transforms that I'll be talking later today, part or all of this is not done. There are plenty of open problems. Stability of reconstruction. Again, you heard this yesterday, that you may have a formula, but if it's unstable, then it's useless because you always have errors in the measurements. If small error in the measurement is going to ruin your inversion process, then your formula is not very useful. And the range description, again, this is something that was talked about yesterday, that your inversion works on the range. In fact, there are obvious examples where you have many inversion formulas, 2, 3 different inversion formulas for the same type of Radon transform. They're different in spirit. They absolutely coincide on the range, and they're completely different on if you get outside of the range. So knowing the range is very important. So these are all mathematical problems that one needs to tackle when they're talking about Radon type transforms. Now I want to talk about some other imaging modalities to justify, to motivate the other types of Radon transforms that I'll be talking about during these lectures. The first one is, the first modality I want to talk about is this ultrasound reflection tomography. It's a very simple, again, sketch. You have a device that works as both an emitter and a receiver. So it sends an acoustic signal and immediately switches to the mode of listening to the echoes. So you send the signal, it propagates like these red spherical waves. There is an obstacle on the way. It hits the obstacle, and then the echo starts propagating back, these dashed green lines. Eventually, the echo reaches the receiver, and the receiver measures the signal. So there are a couple of assumptions I'm going to make. The first assumption is that the pulse radiates isotropically. So in other words, there is no difference in the direction, in this direction, in this, in all directions, it goes with the same spin. The receiver coincides with the source. We already talked about this. This is an interesting assumption that the sound speed is constant. It is very rarely true, but in most cases it is almost true, good enough to have nice images. For example, if they're doing any sort of imaging in soft tissue like breast imaging and so on, this assumption is fairly well satisfied. And then the medium is weakly reflecting. So the last one, by the last one I mean that I will ignore reflections more than once. So if you have an object here, if this thing comes and hits this and then goes and hits the other object and comes back, I'll be ignoring that signal. Weakly reflecting means that more than one reflection is lost, because otherwise my mathematical model would be too complicated. And again, this assumption on one hand is needed for the mathematical model to be simple enough to be solvable, but also it's fairly well workable in many applications. So this is a prototype machine, I think, for breast cancer imaging, where they have this device that the patient lays on the table, and there is this cup where the breast goes, and then this is the device that sends the acoustic signals and then collects the echoes back, and it goes all around this ring, collects the data, and then they try to recover the image.
Which device was this? So normally they take X-rays, right? Or ultrasound?
I'll be talking about. Okay, very good. So So the question was, is why don't they do X-rays, or normally they do X-rays?
Something else actually I've seen. Some other I haven't seen. I've heard of. Other
the Thermoacoustic and Photoacoustic and so on, and then they
I never heard of the acoustic one.
Yeah, so this is something that people are trying to develop right now. I don't think that's why I said it's a prototype. I don't think anybody uses this in the hospitals. So this is probably a good point to talk about this. You will see me talking about so many different types of medical imaging devices, and you may say, what's the point? We already have MRI and CAT scan and this and this. Why do people do this? Why do people keep developing? Every device has its pros and cons, and they are useful in some situations, not useful in some other situations. Currently, in breast mammography, they use X-rays. Very low dose radiation X-rays. That's what they do everywhere. But but it's X-rays. They're ionizing radiation, and there is a huge debate among the doctors, at least in the US. They say among every, say, 100 patients that you screen for cancer, you create cancer in 2-3 by doing this X-ray in the place where cancer was not existing because you're doing ionizing radiation. Some doctors say no, and I'm not anywhere close to be able to judge, but it's debatable. At least everybody knows ionizing radiation is bad. Now, there is MRI, which is, according to, up until now, nobody knows any side effects of MRI. The only side effect of MRI is to your pocket. If you have ever taken an MRI, I played too much football and I tore a ligament in my knee. They did an MRI. Just 15 minutes. My insurance, I didn't luckily, paid $2,500 for an MRI of my knee for 20 minutes. So in the United States, for the breast cancer, the recommendation is every woman above 40 has to screen once a year. Now you can multiply the number, something close to 2,000, by every woman over 40 in the United States, and then you will realize that no insurance company is going to pay that. Right? So then the next thing is ultrasound. It's extremely cheap and no known side effects. After all, pregnant women are doing sonography for the last so many decades. If there was any side effect, people would not do that. The problem with the ultrasound imaging is that the quality of the image is not good enough to catch the cancer early enough. And if you don't catch it early enough, then it's not good. So the way they are thinking of improving this is that they're saying that math, the engineering apparently has, according to them, reached its capacity of improving the ultrasound imaging. They're saying that if anything comes in improving the ultrasound image, it should come from math. And now there's all this super resolution things, this compressed sensing, which is a hot topic, and everybody's trying to get things there and so on. But there is a lot of interest in using ultrasound, improving the quality of something that is an old technique, but for something that people have not been using. Electrical impedance tomography that you heard a little bit about, and you may hear more, is when they put different voltage and they measure current and so on. It has very bad quality of image, but it's very, very good for situations when you have liquid, say liquid in lungs and so on. It can see it very well, whereas other modalities cannot. There is something that I'll be talking about today called photoacoustic and thermoacoustic tomography, which is very, very promising, cheap, and no known side effects, that has the possibility of improving the image, the tomography and so on. So there is need for improvement always. So I'm going to show another ultrasound imaging, but I want to emphasize two things, because tomorrow and in the third, fourth lecture, I will be always talking about the difference. There is a substantial difference mathematically in the situations when the support of your function that you are recovering is inside or outside of the set where you collect your data. So in this setup, the image you're trying to recover is inside here. So you're going to collect your data on the exterior boundary of the domain where your function is. And that's very nice, actually. That has a lot of nice properties mathematically. Here's another thing that people do use. This is in the hospitals. It's called intravascular ultrasound. So, many diseases, heart diseases, blood vessel diseases are because there's all kind of junk collecting in our arteries, unfortunately. And the way people treat this is they want to catch it early enough, and then if there is some need for surgical intervention, they do it. So the way they check is sometimes they put a catheter in an artery. So this is the blood vessel, this is a catheter, this is the cross-section. And then this catheter has ultrasound emitters and receivers, so they send signals, and then they receive echoes, and then they try to recover the image. They try to image the walls of the vessel and all this clot and see how much of it is closed. Now, the difference here is, look, you're collecting the data here, but your function is outside. So it's what people call exterior problem. There will be a lot of difference between interior problems and exterior problems. It turns out that the exterior problems are very unstable. There's very little thing that you can recover stably. Luckily, the parts that you can recover stably are more or less what you're looking for in these images. And maybe Professor Bowman will be talking about that, and I will definitely touch upon this. which wavefront sets you can see and which wavefront sets you cannot see in this setup. And it turns out that the wavefront sets that you can see are good enough for people to be able to do some judgment medically. Okay, so where am I going with this as far as the radon transforms are concerned? So look, let's do this ultrasound reflection tomography but on a sketch. So this is the device that sends and receives signals. So if I send a signal, the signal propagates, hits an obstacle, and the echo starts propagating back. If I'm assuming that it's the sound speed is constant, I measured the time when the echo came back, and I know the sound speed. The distance should have been traveled twice. So I know the distance that my signal traveled. It went there, came back, and I know the time, and I know the speed. So I know that the distance from my object to the obstacle is t times c over 2. A very simple thing. What I don't know is, okay, I know the distance, but there's too many locations at that distance. If I'm standing here and my eyes are closed and you're saying there is an obstacle 2 meters away, is that there, or there? I don't know. So in fact, imagine that there are obstacles, several obstacles at that distance. Imagine there was one obstacle here, one here, and one here. What happens? Well, you get all the echoes simultaneously. This guy, at that moment, simultaneously gets all the echoes back. And if you have a continuum of such things, then what you're measuring really is you're measuring the integrals of this reflection coefficient along points that are on the same distance, which in the 2D would be integrals along circles, in the 3D would be integrals along spheres. There is a way to get the same thing. If you honestly write down the wave equation and do your math, you will see this integrals along spheres in a very rigorous way. I just wanted to give you some sort of a hand-waving feeling where this integrals along spheres come. And again, the goal here is to recover the shape, the size, the location of the object. So I want to recover that function, but I don't know the function. I know its integrals along circles. So that motivates this second type of radon transform that I was talking about, which is called the circular radon transform if you're in 2D, or if you're in 3D, it's called the spherical radon transform. And what this transform does is, given a function, let's say we're in the plane, given a function of 2 variables, it puts into correspondence to that function its integrals along spheres, centered at point P and of radius R. Now, this is again the right moment of doing this complexity count. Let's see, guys, how much data do I have and what kind of function do I try to recover? If I'm in the plane, the function I'm trying to recover has 2 parameters, the 2-dimensional variety. The data that I'm measuring there are such circles, right? How many parameters do I need for all the circles in the plane? 3. 2 parameters for the location of the center and 1 parameter for the radius, right? So theoretically, it looks like I have 3 parameter data that has 3 degrees of freedom, and I'm trying to recover a 2 parameter function. So the problem seems to be overdetermined. I have too much data, which is not necessarily bad. I mean, you can never have too much data. It always helps. But if you think about the applications, guys, the location of the center is the microphone. That's where you put the microphone, or this device, the transducer. Now, if I'm trying to recover the interior of the patient, I cannot put the microphone in the interior of the patient. If you got the patient to put the microphone, you may as well check what's going on and forget about imaging, right? So the way we will set up the mathematical problem is we will assume that in 2D, the set of the microphones, the set of the centers of the circles, is limited to a curve. Let's say you put them all along my body, then you would say that the centers are limited to a circle, the red circle. You're trying to image inside here. You have one parameter for the location of the center, for example, polar angle. And the other parameter would be the radius of the circle. Then the radius, again, corresponds to the time that it took you to hear the echo, and the other one is the location. In the other problem with the intravascular things, you would have the same thing, but the image would be outside. So this is the interior problem. The exterior problem is when the function is outside. Or you can have some linear detectors, so you can put things like this along my body like this and try to image inside along the straight line and so on. Now, some choices of sets for the microphone are good, some are bad. And that's another mathematical problem of which ones are good, which ones are bad. Again, we have the same set of problems. Uniqueness, do I have uniqueness or I don't? Reconstruction formulas, stability, range description, just the same things that we had before. And let me see. Okay, so that's another modality. I'll be talking about that in a minute. But just to show you that it's not so trivial with the uniqueness, we have two situations here on the. I have two choices. One choice is for the microphones, is to put them along a straight line, and the other choice for the microphones is to put them along a circle. If you were the one to choose, which one would you choose? Everybody chooses circle. Why? I would always choose line because it's somehow easier. I mean, it's right. I mean, what can be easier than something? Yeah, well, you're smarter than I am, guys. So, the circle is the better choice. The line is not a good choice. The reason for it is, you see, if you're sitting on a line, why is line a bad choice? If you're sitting on a line and you're measuring the integrals of a function, say supported in the plane, or it's a portion of the plane, you measure the integrals and you are trying to recover the function, it is easy to see that there is no unique recovery. Your kernel, the kernel of the transform is huge. There are plenty of functions that are not zero, but the integrals of this type are zero. Can anybody give me an example of a function that is not zero, but the integrals along all these circles are zero? 1 at the top minus 1 at the bottom, right? Or anything odd with respect to the line. Any function that is odd with respect to the line, it would be dead if you integrate along circles like this. So then you don't have uniqueness because you have infinitely many functions that give you zero, but the functions are not zero. So this is a very important mathematical problem. Can you describe the curves that give you uniqueness and the curves that give you non-uniqueness? In fact, that's one of the very nice results that I'll be discussing tomorrow due to there's a complete solution for the 2D case. Describe all the bad ones and all the good ones. For the two-dimensional case for functions that are smooth and compactly supported, there is a very nice result by Mark Adornowski and Todd Quinto that I'll be discussing tomorrow. And the similar result for higher dimensions is not known. There are some conjectures, but the full result is not known. And the similar result for functions that are not compactly supported, you can assume as fast of a decay as you want, exponential decay, for example. The full result is not known. So if you're looking for a nice problem to work, there it is. So describe all the sets, say even in 2D, where assuming that your function decay exponentially fast, it classified all the curves as bad ones and good ones. There's a conjecture, but the proof is not known. There are plenty of pieces, necessary conditions for something to be good or bad, and sufficient conditions, but they don't match. Okay, so here's another modality. This is something dear to my heart. That's why I want to talk about it. I did my dissertation on this topic, and it's very, very hard. Several people believe that one day, very soon, this thing may bring a Nobel Prize. So, and one of the guys that is really, really big in this was on my PhD committee, and I have a couple of papers with him. So, if he gets a Nobel Prize, I'll have a paper with the Nobel Prize winners.
Is he a doctor?
Huh?
Is he a doctor? Or
he is a biomedical engineer.
Okay, then you have a chance.
Yeah. Yeah, Leon Wang, he's probably the biggest guy nowadays in this field. So what is this guy? I'm going to describe it for you, and then I know that when you start hearing about this, you're going to shake your head and say, "Oh yeah, that's science fiction. Good luck," and so on. And then I'll show you images. So here's how this thing works. So again, think about this as being a cross-section of a human body. It's called thermoacoustic. We're going to use two different types of signals. Remember at the beginning I said that the physical nature of the signal gives sometimes a name to the tomography, so I have two different physical types of signals, thermal and acoustic. So what we do is we heat up the tissue by sending microwaves through the body, just like you heat up assembly or whatever, in the microwave, right? You send microwaves through the body and it heats up the tissue. slightly by 1 point of a degree or something like that. You don't cook the patient. So what happens is the doctors have realized that there is a huge contrast in the amount of energy absorbed. Different tissues absorb differently. Muscles absorb different amount of energy. Fat absorb different amount of energy. In fact, it turns out that cancerous cells absorb 5 times more energy. There is a 500% contrast. The difference between the heat up of the tissue is very, very big. And then what happens when objects heat up? They expand. And this expansion creates a pulse, acoustic pulse that radiates. And then they put a microphone on the edge of the body, and then they listen to the signal that comes out. So again, the process is send microwaves, heat up the tissue, there's a noise coming outside of the body, from inside the body, and then you listen to that noise. Then you try to recover the image. There is a very, very old classical problem in inverse problems called, can you hear the shape of the drum? It has something related to the spectral theory and so on. Well, some people call this problem, can you hear the heat of the body? Because you're heating up the body and then you're listening to the noise coming out of it. So then the question is, can you use that information to recover the image? Okay, so again, we'll assume that the sound speed is constant. Now this is an image, guys, made by Robert Kruger, who was one of the first guys who came up with this idea of using it for imaging. He made a device in his garage, basically. I mean, there are YouTube videos of his lab. If you look at it, it's really like, literally like doing things in the garage. And this is, something that, by that I mean this is not optimized by any means. And if you have ever seen any images of, say, mammography, you will see how you can, you would notice that this is image of an amazing quality for something that a guy did by his hands. If you go to any sort of normal lab like GE or Siemens and do it on a careful base, you can dramatically improve the quality. And this is probably one of the first images by something that a guy made with a hammer, basically. Here's an image of the same technology of a hand, of this piece of the palm of the hand, and you can see all the blood vessels. This is done in London, by a group in London, and this is about 5 millimeter thick. The resolution here is 1 millimeter, and you can see the blood vessels at the level of 1 millimeter thickness. Nowadays, I have seen results where they claim they can go all the way to nanometers with this technique. So the contrast and the resolution they can get with this technique is absolutely amazing. The reason for this is the classical example of so-called hybrid imaging techniques. Now, next week, Professor Peter Cushman, who is my former PhD advisor, will be giving a series of lectures on hybrid imaging techniques. You will hear a lot about this, and I'm absolutely sure you'll see plenty of other pictures. The hybrid imaging techniques are the techniques that use different types of signals. As I said here, people use thermal and acoustic. The reason this hybrid imaging is good is that every physical wave has its pros and cons, has its pluses and minuses. And if you can combine them in a smart way to get the strength of each, then you are in a really great shape. So everybody knows that the optical tomography, or things that are related with microwaves, or even there is another tomography called Photoacoustic where they do pretty much the same thing, except they heat up the tissue with the laser. So people know that optical tomography has a very good contrast, but it has a very, very poor resolution. Ultrasound tomography, on the other hand, has a very good resolution but very poor contrast. So if you combine the two in a smart way, then you can get the good contrast and good resolution simultaneously, and that's why you get such great images. Contrast, guys, again, is the difference in color, basically, between different types of tissues. How much is the bone different from muscle? Is it really black and white, or slight shades of gray and so on? And the resolution is what is the smallest piece that you can see. In imaging, most of the time, it's a payoff. When you improve one, you decrease the other, and so on. But in hybrid imaging, people are able to combine good things of both. Another imaging that is related to the spherical or circular radon transform is synthetic aperture radars. This is when the airplane has a radar, it flies over the ground and it tries to image the ground. Either you're looking for enemy tanks hidden under the bushes, or You're trying to see deforestation, if somebody is cutting the trees, or something else, whatever you're looking for. So what they do is they send the airplane, the radar on the airplane sends these signals, and they propagate as spheres. And then when they reach the ground, let's assume in the simplest case that the ground is a perfect plane, you're going to get the echoes. So it's a spherical wave. It doesn't touch the ground, at some point, it just touches the ground. And the intersection of that sphere and the ground is just one point. When the radius of the sphere starts growing, the intersection would be a small circle, a larger circle, and that's the set from which you're getting reflection. Right, so you're getting reflections from the ground along concentric circles. And then when the airplane keeps flying, you get concentric circles centered on the projection of the trajectory of the plane. And you're trying to recover the image on the ground. And this is a picture from the book by Margaret Cheney and Brett Gordon on radar imaging. Very nice book if anybody is interested for math of radar imaging. You can see that the airplane is flying and you collect the integrals along circles and you're trying to recover the image. Again, the task here is to invert the circular Radon transform. This is something slightly different, and it brings another type of Radon transform. This is what people use to find oil at the bottom of the ocean. See, there's a boat that is going on the surface of the ocean, is throwing behind it an array of microphones, a transducer, and then they create a small blast. Most of the time they blow up something, create a noise, and that sound propagates. Some of it reflects immediately from the bottom of the ocean, some of it goes through the mud and reflects from some rock layers, some of them go even further and reflect from the layer between rock and, say, I don't know, oil, and some of it goes further and so. So the echoes come and the echoes are recorded here. Now, let's assume that you have just one receiver here. Forget about the others. So you have the source and you have the receiver. Let me make a picture here. So you have the source and you have the receiver, and you know the time that passed, and let's assume you know the speed of propagation. So by knowing the time and the speed, you know how much distance the signal traveled, and it reflected once. So, if this is D1 and this is D2, you know this quantity. This thing is fixed. This D1 plus D2 is fixed. But you don't know where this thing happened. And in fact, if there were several locations with the same D1 plus D2, the signal would come at the same time. So what would be the set of points, guys, such that the sum of the sum of the distances from the given point to two points is the same? Ellipse. And what you're doing is you're really recovering integrals of the reflection function along ellipses. So almost exactly as the previous problem, we did just one simple thing. In the previous setup, I was assuming that the emitter and receiver are at the same place. They're the same device. But first of all, it's very hard to manufacture. Secondly, it's not natural, right? I mean, most of the time your source may be far away and so on. And I'm not even talking about situations when you don't want your receiver to be known. Let's say you're collecting data, you're in the enemy fire. The source may be somewhere which is protected. The receiver is you. If you tell everybody where you are, you won't last long, right? So you may want to be secret for your receiver, and the emitter is flying somewhere protected or far. And as soon as you separate the emitter and receiver, you immediately, instead of circles, you get ellipses. And the line becomes very quickly very complicated. The circles have so much of symmetry that you can do a lot of nice math, which you'll see tomorrow, which you cannot do with ellipses. And this brings again, you can do the same thing, by the way, in medical imaging. Receiver and emitter, and this distance is constant. So this brings us to the definition of the elliptical Radon transform, that given a function, let's say again we're on the plane, although you can do that in 3D, and you get ellipsoids of rotation. Given a function, the elliptical Radon transform, and in my slide the elliptical will be with the tilde, puts into correspondence to a function its integrals along ellipses. Again, we can very quickly do this complexity count I'm trying to recover a function of two variables on the plane. What's the dimensionality of the variety of ellipses on the plane, guys? How many degrees of freedom is the family of ellipses, does the family of ellipses have? I'm going to give, or no?
Eccentricity and the two.
Well, okay, let's look. This is the location of the emitter, this is the location of the receiver, and there is the, well, not the radius, but whatever that D thing, right? 5. 2 for this, and 1 this. So you have 5-dimensional data, but you're trying to recover a function of two variables. That's great if you can collect all that. But again, you probably were not going to be able to collect that in medical imaging. Like, let's say if you were doing it on a patient with separate emitter and receiver, your emitter and receiver would be limited to a curve, and you still can drop the dimensions a little bit to have a right amount. For example, we have been looking at some problems with Venki where the distance between the emitter and the receiver is fixed. So by knowing the location of receiver, you immediately know the location of the emitter if the curve is fixed and the distance is fixed. And the other parameter would be the radius or whatever the distance thing, and that would be it. So, and there's many other ways. So this problem is very, very little studied, I should say. There are very few results in this field. Maybe no more than 10, I would say. I don't know if Venki knows anymore. One of the papers is with Jan Bowman, Venki, and I, and Todd Clinton. There's a couple of others with some of our colleagues. Cliff Nolan has done some work on it, who will be speaking here. But most of the problems that I talked about are not known. For example, the description of injectivity sets, the description of the range, exact inversion formulas are not known. Most of the formulas are approximate with this microlocal approach and so on, about which we'll be talking about later. So, very, very open area of research. And for the next whatever amount of time I have left, 6 minutes, I want to talk about the last type of radar transforms that I want to talk about this week. This transform is very interesting. It's actually different from the previous 3 substantially for certain properties. And it comes from a different type of tomography, but you have seen some of this today, some of the math I'm going to talk about. So this is a single scattering optical tomography. So it's optical tomography. You are shining light through the body. And single scattering means that I'm going to assume that the photons would scatter once. So I will assume that the thickness of the object is such that one scattering is all that you get. Now, it may fly through, of course, but you don't get more than one. If you do, then we ignore it, basically. So here's what the assumptions are. So I'm again trying to image the interior of the object. We're going to use light. The light would either transmitted, that flies through, or scattered, and if it's scattered only once. Modical optical thickness, majority of photons scatter once. We're going to use collimated emitters and receivers. So collimated means the following, guys, that my emitters and receivers are such that they would only, well, the emitter would shoot the photons along straight line. That's clear. It doesn't shoot like a shower. It shoots along straight line. And the receiver is such that it gets photons only coming from this direction. So, for example, if it comes to the receiver like this, under a certain angle, it will not be registered. So that's what collimation means. And the task here is to recover the light absorption coefficient. Some light will be absorbed inside. This is exactly related to the radiative transport equation that Professor Rakesh was talking about today. Sometimes people try to simultaneously recover the absorption and the scattering coefficient, but that's very hard. So I'll be talking about today recovering the absorption, knowing the scattering. Again, the light goes, some part of it is scattered, some of it absorbed, so it heats up the tissue and the photons don't go further, and some of it eventually reaches the receiver. So here is, oops, again too much. Okay. So here is the radiative transport equation that you saw today. There are some differences that I want to talk about. So first of all, this is a time-independent radiative transport equation. So you don't see that whatever was U in the formulas that Professor Rakesh was showing is I here, that's the intensity. You don't see that term. There was a term that was u prime t, that related with respect to t, that's gone because I don't have time dependence. Mu of A is the absorption coefficient. Mu S is scattering coefficient. Again, scattering, and I have the same variables, R and S. R is the radius vector, it's the location about which I'm talking about. S is the direction. So the particle flies at any given moment of time. The particle is in a certain location, and it has a motion in a certain direction, right? R is the location, S is the direction. So it's a balance equation. This radiative transport equation is just about the balance. So it says that the intensity at location R and S is lost in the following way. This much is lost to scattering. So the intensity depends again on the location and direction. This much is scattered. This term corresponds to the absorption, heating of the tissue. This is what moves. And this is again the term that you have there. A S hat prime is the probability of the particle that flies in the direction of S prime to be scattered in the direction of S. Okay, that's not good. So you see, if you're at this location, you have the particles come and go. Some particles, this is the location in the right direction. Some particles are scattered away. Some particles are absorbed. They are killed here. Some particles continue their travel, but it is possible that there was a particle that was flying in the wrong direction, but it's scattered here and it's scattered into the right direction. So you may gain. Somebody was flying in the wrong direction, and then by a chance it's scattered, and now you're gaining that. Right? You're not only just losing, but you're also gaining. So this part corresponds to gaining by particles flying in the wrong direction, scattering in the right direction, and this is probability. So this thing is normalized. So if you take the integral of A with ds prime without any weight, you will get 1, so on. So then you can have the condition on the boundary. You're assuming that you know the light that you're shining into the body. Okay, so then, by the way, I should say that everything I'm writing here refers to this paper. If anybody is interested in the details of the physics, and I'm going to skip a substantial step where you go from the PDE formulation to the integral geometric formulation. If anybody is interested in details, this is a great paper. There is a follow-up paper in the same journal. It's 2 pieces. So by Lucio Florescu, John Shotland, and Vadim Markel. So if you, now that was the general setup. If you assume that we have a slab, a rectangular domain, and this is how the ray comes in. You remember we have correlated emitters and receivers. So if I send the ray from the location R1 in the direction S1 hat, and then my receiver at the location R2 registers photons coming in the direction of S2, then you can reformulate this PDE problem using Born approximation to something that is an integral geometric problem. So this part is something that you can get from the measurement. So you can assume this left-hand side to be known. Mu t is attenuation. Attenuation coefficient is a sum of absorption and scattering. So a portion of this is known. It's a sum. So basically, you can think of this as being mu a. This is something that I'm looking. And scattering is, I'm assuming I know. So I know this. And for all practical purposes, you can assume that it's mu a, the absorption. So by knowing this and this, what I know is I know the integrals of the function that I'm interested in along the trajectory. BR stands for broken ray. So the broken ray is this trajectory that corresponds to the location, direction, location, direction. So if you're in the plane, by designating a location on the left boundary of the slab and the direction, and a location on the right boundary in the direction, you uniquely define a broken ray. And if you do those measurements, it turns out that your mathematical problem of imaging boils down to inverting a generalized Radon transform integrating along the broken rays. So this is the incident beam, this is the outgoing thing, you're trying to recover a function defined in this domain from trajectories like this, from broken ray trajectories. You enter here, break here, enter here, break a little further, enter here, break a little further. And you can see that, again, dimensionality count is, if you allow different angles of breaking and different heights and so on, it's an overdetermined problem. What one can do to, for example, fit the dimensions, and that's what's done in this particular paper, is they are assuming that the angle of breaking is fixed. That doesn't mean that the photons don't fly at different angles. That means that they ignore them. Their detectors are collimated so that they are measuring only photons coming under the same fixed angle. In that case, you have a two-parameter family. One parameter corresponds to the entrance height, and the other parameter corresponds to the distance that it travels before it scatters. Again, we do not assume they scatter on the same angle. We simply collect the data only corresponding to that angle.
You are assuming that there is a single scatterer in every slab.
Exactly. Yes. Yes. I mean, again, there certainly is more, but we are measuring only the single scatterer. Yeah. Yeah.
So each scatter.
Yes. Well, in this case, they say that it's about the thickness of the object. So actually, there was a word that I didn't address. It's called, you see, it says mesoscopic radiative transport. In fact, these guys are physicists. Well, John is at the math department, but he's a very good physicist in addition of doing good math too. So the word mesoscopic stands for being in between. So if your slab is very thin, then you only have the ballistic regime. Somebody was asking about regimes today in the radiative transfer equation. The ballistic regime means that your object is so thin that the photons fly through. They don't have a chance to scatter, or most of them don't. If your object is very thick, then you're in this diffusive regime, where people use the diffusion equation instead of the radiative transport equation. Sometimes, or I don't know. But the mesoscopic regime is that you're falling between the two. You're not quite in the diffusive regime yet, but you're not in the ballistic regime. So you're somewhere in between, and this in-between thing, they are assuming that the optical thickness is such that the predominant amount of particles scatter exactly once. Now, Vadim Markov recently had a paper on something called star transform. I haven't had a chance to look at the details, but I think he is assuming that it's a couple of breaking points. So it's not just one, but it's still traceable. It's not too many to be lost and go to diffusion. In this particular case, the SSOT, the single scattering optical tomography, the assumption is that the thickness is such that it scatters once. And that brings us to the definition of the, some people call it broken ray radon transform, and some people call it V-line radon transform. I like the V-line more because it looks like a letter V. The broken ray also stands for multiple breaking, so this one is a little bit more rigorous. The V-line radon transform takes a function of two variables, again if you read the plane, and puts into correspondence its integrals along broken rays, breaking once. And the task is the same as before. There is another imaging modality that I probably will talk about tomorrow. I'll stop here. I'm out of my time. And I'll start with properties of the radon transform tomorrow. Mathematical properties.
Are you assured of straight lines? Are you assured of V being straight lines?
Well, in the model, I'm assuming they are. Now, how much that corresponds to physics again is. I would let John answer that question.
So one announcement, there is a sign-up sheet up in the front for the day trip on Saturday. If you're interested, the deadline is 5 p.m. tomorrow. So by the time you should let us know so that we can arrange suitable transportation.
Where are we going?
The consensus seems to be Mysore. Okay.
No, we don't have So it depends on what you mean by that. So if you sample reasonably well, there's two types. One is by all you mean the whole continuum. Of course, that's not possible. Models have to discretize, right? Now, if your discretization is uniform,
It depends. Those numbers are
not
not
facing
easy
each
to
other
test.
at angles,
You're checking.
then that's reasonably good.
This is a look and take.
No, I would
You are saying how many say in a small area.
Elliptical.
But then you make it's not like never know.
So I want to see the same problem.
You can't stop for 2, 3 maybe 2 seconds.
Very different angle and the straight line that we are. So we need all angles or all straight lines. Or some is enough to calculate that if I
You will have to also say what cluster functions. If you don't limit the cluster functions, the answer is you have to. If you miss out something, I can write the counter example.
So let's say it's
Smooth is not good enough. So, for example, the support is important. So, for example, there are these are so-called problems. They're a huge area of research, and depending on what you miss, you may or may not get it. Because, for example, there is